What if some computers could calculate without using the familiar ones and zeros we associate with computers today? Long before modern PCs became common, engineers created machines that used gears, electrical signals, moving parts, and even flowing fluids to represent information and perform calculations. These machines are known as analog computers. In this video, we're going to explore 10 important types and examples of analog computing, from simple devices like the slide rule to powerful machines used for scientific simulation and control. Mechanical analog computers. Mechanical analog computers used physical movement to represent and process information. Instead of electronic signals, they can use gears, rotating shafts, wheels, levers, cams, and other mechanical components. The position or movement of one component can represent a changing value, while another mechanism performs a mathematical relationship with it. The basic idea is surprisingly simple. Imagine a rotating shaft representing the speed of an object. If that shaft turns faster, the represented value increases. By connecting several mechanical parts together, engineers could create a physical system that behaved according to a mathematical relationship. Mechanical analog computers became increasingly sophisticated over time. Some machines could add or subtract values, perform multiplication through gear ratios, or integrate changing quantities using specialized mechanical mechanisms. These systems allowed engineers to solve problems that otherwise would require extensive manual calculations. Although mechanical analog computers look primitive compared with modern computers, they were remarkable engineering achievements. They proved that physical motion itself could be used as a form of computation long before electronic processors became practical. Electronic analog computers. Electronic analog computers represent information using continuously changing electrical signals, commonly voltages. Components such as operational amplifiers, resistors, capacitors, potentiometers, multipliers, and integrators can be connected together to represent mathematical relationships. For example, one voltage could represent the speed of an aircraft, while another represents its position. As the voltages change, the electronic circuits process those signals continuously. The output voltage then represents the result of the calculation. Electronic analog computers became much faster and more flexible than many mechanical systems. Instead of waiting for large gears and shafts to physically move, electrical signals could travel through circuits almost instantly. This made electronic analog computers extremely useful for real-time simulation. These machines were especially important in engineering, science, aircraft simulation, and control systems. Although large general-purpose analog computers became uncommon as digital computers improved, electronic analog computing remains an important concept in modern electronics and specialized computing research. Slide rules. A slide rule is one of the simplest and most famous examples of a mechanical analog computing device. It uses specially designed logarithmic scales that allow users to perform multiplication, division, powers, roots, and other calculations by physically moving one scale against another. The interesting part is that the slide rule does not calculate in the same way as a digital calculator. Instead, the physical position of the sliding scale represents the mathematical relationship. The user aligns the scales and reads the resulting position to obtain an approximate answer. For centuries, slide rules were important tools for engineers, scientists, students, and other professionals. They were small enough to carry around and did not require batteries, electricity, or a computer program. With enough practice, an experienced user could perform calculations surprisingly quickly. Slide rules eventually became
largely obsolete when electronic calculators became inexpensive and widely available, but they remain an excellent example of analog computing because they demonstrate how a physical arrangement can represent mathematical relationships without using binary numbers.
Differential analyzers. A differential analyzer is a specialized mechanical analog computer designed to solve certain types of differential equations. These machines used mechanisms such as rotating disks, wheels, shafts, and integrators to physically perform mathematical operations. One of the most famous examples was the differential analyzer developed by Vannevar Bush and his team at MIT in the early 1930s. It was a huge machine compared with today's computers, with interconnected mechanical components working together to represent mathematical variables. The machine was particularly useful for problems involving changing systems. Engineers and scientists could configure the mechanisms to represent equations and then allow the machine to physically perform the calculation. This made difficult mathematical problems much more practical to study. The differential analyzer became one of the most important milestones in the development of modern analog computing. It demonstrated that a machine could directly model complex mathematical relationships and helped establish analog computers as serious scientific and engineering tools.
Hydraulic analog computers. Hydraulic analog computers use the movement, pressure, and flow of liquids to represent variables and perform calculations. Instead of using electrical voltage or mechanical gears as the primary representation, the system uses physical properties of fluids to model mathematical relationships. A simple way to understand the idea is to imagine water flowing through pipes and collecting in containers. The rate of flow, pressure, or amount of liquid can represent a variable. By changing the arrangement of pipes, valves, and containers, engineers can create relationships between those variables. Hydraulic analog systems were particularly useful for modeling physical processes where fluid movement was already important. They could be used in engineering and control problems where pressure and flow were naturally connected to the system being studied. These systems show just how broad the idea of analog computing really is. An analog computer does not have to look like a traditional electronic machine. If a physical process can represent variables and their relationships, that process can potentially be used for computation.
Pneumatic analog computers. Pneumatic analog computers use air pressure and airflow to represent information and perform calculations. Instead of electrical signals or mechanical movement, changing pressure and fluid flow become the physical quantities used by the computing system. The principle is similar to hydraulic computing, but the working medium is air or another gas. Valves, pressure changes, pipes, and other pneumatic components can be arranged so that the behavior of the system represents mathematical relationships. Pneumatic computing became especially interesting for control and industrial applications because compressed air could operate equipment in environments where electrical systems might be less suitable. The computing process could be connected directly to physical control systems. Although pneumatic analog computers are not something most people encounter today, they demonstrate an important idea in computing history. Information does not have to exist as electrical bits. Pressure and airflow can also carry information and participate in computation.
Planimeters. A planimeter is a specialized mechanical analog computing device used to measure the area of an irregular shape. It's especially useful when the shape cannot easily be calculated with a simple mathematical formula. To use a traditional planimeter, an operator traces around the boundary of a shape on a map, drawing, or plan. As the tracing arm moves, the mechanical mechanism continuously integrates the movement and produces a measurement corresponding to the enclosed area. What makes the
planimeter, an analog computer, is the way physical movement represents and processes the mathematical quantity. Instead of entering coordinates into a digital program, the device physically follows the boundary and performs the calculation through its mechanical mechanism. Planimeters were useful in fields such as surveying, engineering, cartography, and architecture. They're a great example of how analog computing could solve a very specific real-world problem using a simple but clever mechanical design.
Tide predicting machines. Tide predicting machines were special-purpose mechanical analog computers designed to predict the rise and fall of ocean tides. They used mechanical components to combine different repeating patterns associated with tidal behavior and produce predictions for future times. One famous machine was developed from the work of William Thomson, later known as Lord Kelvin, in the 19th century. The machine used a system of pulleys, wires, wheels, and other mechanisms to combine tidal components and generate predictions. The importance of these machines went far beyond simple mathematics. Accurate tide predictions were valuable for navigation, coastal planning, and maritime operations. Before modern electronic computing, mechanical tide predictors could dramatically reduce the amount of manual calculation required. These machines are a fascinating example of special-purpose analog computing. They were not general-purpose computers like modern PCs, but they were extremely effective at the particular problem they were designed to solve. Analog flight simulators. Analog computing was also used to simulate aircraft behavior. Flight simulation requires many variables to change continuously, including speed, altitude, direction, acceleration, and control inputs. Analog computers were well suited to modeling these changing relationships in real time. An analog flight simulator could represent the behavior of an aircraft through electrical or mechanical signals. When a control input changed, the corresponding signals changed as well, allowing the system to model how the aircraft should respond. This technology gave engineers and pilots a way to study aircraft behavior without having to perform every experiment using a real aircraft. It could also help engineers test control systems and study how different conditions might affect flight. Modern flight simulators use vastly more powerful digital technology, but analog computing played an important role in the development of simulation. It showed how a computer could continuously model a complex real-world system instead of simply performing isolated calculations. Analog process control computers. Analog computers were also used for process control, where a computer continuously monitors and influences a physical system. These systems could work with variables such as temperature, pressure, flow, speed, or electrical conditions, and respond as those values changed. For example, an industrial process might need to maintain a particular temperature. An analog control system could receive a continuously changing signal from a sensor, compare it with the desired condition, and produce a control signal that adjusts the equipment. This approach was valuable because analog systems could respond continuously to changing physical conditions. They did not necessarily need to wait for a long sequence of digital calculations before producing a response. Modern industrial control systems are generally much more sophisticated and often combine digital computers with analog sensors and control electronics. But the underlying concept remains important. Measure a changing real-world condition, process that information, and respond to the physical system.
If you enjoyed this video, subscribe to ByteSimple for simple explanations of computers, technology, AI, and more. And in the next video, we'll explore digital computers. See you there.